Alright, so as our first quantum error model, let's consider a simple case, a very simple model called 3-qubit bit flip code. 3-qubit bit flip code. And let's follow the traditional communication names, namely Alice and Bob. So suppose that Alice wants to send some quantum information through some faulty communication channel to Bob, and we assume that the faulty channel has the characteristic of the bit flip error, the bit flip model, and the qubit gets flipped with probability p, and it's left unchanged with probability, let's say, 1 minus p. Okay, so now assume that Alice wants to send, so Alice wants to send qubit phi A0 plus B1 for some unknown values A and B through the bit flip noise channel. Okay. So now what we do here in this protocol is that Alice prepares two more qubits, ancillary qubits, okay, each set to state 0. So we have the state that Alice wants to send. This is phi. And we have two more qubits, ancillary qubits. So we have a 3-qubit code. Okay, this is where the name comes from. And then Alice codes her single qubit state into a compound state of three qubits, and using two CNOT gates. Okay. So she's going to use, this is the encoding procedure. She takes the first qubit as a target qubit, the control qubit, sorry. She takes the first qubit as a control qubit and applies the CNOT transformation on the second qubit. And then she also takes the first qubit as the control qubit and applies the CNOT transformation on the third qubit. So this is the encoding stage. So our qubit phi is encoded into a 3-qubit state. Okay, so then this encoded state, the 3-qubit state, is introduced to the error model, the bit flip error. Let's call it E bit. Okay. Okay, and then these three qubits are sent to Bob. Okay, and Bob, what he's going to do is that he's going to decode this compound 3-qubit state. But he also likes to know what kind of which qubits were subject to the error. So he'd like to know the information about the error, that which qubits got corrupted during the transmission. So for this, he's going to prepare two auxiliary qubits set to 0 initially. Okay, and then he's going to take the first qubit as a control qubit, and then he's going to apply a CNOT transformation on the first qubit of the ancillary qubit. And then next he will take the second qubit. He's going to take this as the target qubit and then again, he's going to apply another C0 transformation. And next, he's going to take the first qubit as the control qubit, and then this goes to the second qubit. He's going to apply C0 transformation. And finally, he's going to take the third qubit here as the control qubit, and then this goes down to the second qubit of the ancillary states. So this is the correction stage. So here, actually, this is called the last qubits. Last two qubits are called the error syndrome. The error syndrome gives us the information about the error occurred on the qubits. Okay, and then Bob will respectively accordingly apply a decoding operation in the receiving end. He will take the first qubit as the control qubit and apply a C0 transformation on the third qubit of the three qubit encoded states. And then next he's going to take the first qubit again and then apply a C0 transformation on the second qubit. This last part is called the decoding stage. Decode, this is the correction. Okay, so since we have the bit flip error model, then the correction will also be a bit flip transformation applied to one or none of the qubits. Okay, and this will leave Bob with a single qubit in state of phi with probability 1 minus big O p squared. All right, so let's see how this works. All right, so Alice then wants to send let's say a 0 plus B1. So then with the additional qubits, the joint state, the joint 3 qubit state becomes a 0 plus B1. And then we have the 2 qubits ancillary states 0, 0, right? So this is equal to A 0, 0, 0 plus B 1, 0, 0. So this is a compound state, okay? Now Alice encodes the state by applying a C0 transformation. After the decoding stage, we get after the encoding stage, so the first part remains the same, A 0, 0, 0, and then we have B 1, 1, 1. So essentially, ket 0 is encoded by the logical bit 3 qubit state 0, 0, 0, right? And ket 1 is mapped to the encoded state 1, 1, 1. All right, so now Bob receives the 3 qubit state through the faulty channel or the noisy channel. And then he will receive the 3-qubit state either with no errors or a state where only one qubit is corrupted or 2 qubits are corrupted, or maybe all qubits are corrupted, maybe. So let me draw a table to denote these. State, probability, and change. All right, so now if Bob receives a 0, 0, 0 plus B 1, 1, 1, so we're talking about the first 3 qubits of the system. If Bob receives a 0, 0, 0 plus B 1, 1, 1, well, the probability of Bob receiving this state is 1 minus P cube, right? So in this case, there is no error, so no change. Nothing's changed. This is exactly what Alice tried to send. If we have A 1, 0, 0 plus B 0, 1, 1 in the receiving end, that means only the first qubit is changed, right? The probability of this occurring is P times 1 minus P squared. So only the first bit is changed in this case. It could be that maybe 2 qubits are corrupted. So if Bob receives something like a 0, 1, 0 plus B 1, 0, 1, so in this case only the second qubit is changed, and we have, so this occurs with probability the same as earlier, P times 1 minus P squared, so only the second qubit is changed here, second bit. If Bob receives a 0, 0, 1 plus B 1, 1, 0, so that means only the first qubit is changed, but it could also be that 2 qubits are changed. Maybe the first and second bits are changed. So if Bob receives a 1, 1, 0 plus B 0, 0, 1, and the probability of this happening is P squared 1 minus P. So in this case only the first and second bits. Another case would be that first and third bits are changed. So A 1, 0, 1 plus B 0, 1, 0. The probability of this having this state is the same, P squared times 1 minus P. And next, maybe second and third qubits might have changed. A 0, 1, 1 plus B 1, 0, 0. And then finally, maybe all qubits are changed. So this entire state given here might have changed during the transmission. But the probability of this happening is p cube, all bits. All right, so now Bob prepares two more qubits, ancilla qubits, both set to 0. And Bob's going to use these qubits to gather information about the error. Okay. And after applying the C0 gate, the compound 5-qubit state, so there are 5 qubits in total in the system, right? So after applying the C0 operation here, I'm going to modify this table. So in this case, the last 2 qubits will be 0, 0. In this case, we have 1, 1. Here we have 1, 0. And here we have ket 0, 1. This is 0, 1. And here we have 1, 0. 1, 1. And lastly, we have 0, 0. Okay, so next Bob measures the 2 ancilla qubits in the canonical basis. Okay, and essentially what we get is basically 2 classical bits of information. So this is what we call the error syndrome. It's the information about the error. Now, if Bob measured syndrome on one side and the action that Bob takes. If Bob measures 0, 0, then Bob does nothing. I'm going to explain why. But if Bob measures 0, 1, then he just flips the 3rd qubit. Flip the 3rd qubit. If Bob measures 1, 0 in the error syndrome, then he flips the 2nd qubit. If he measures 1, 1, then he flips the 1st qubit. So, okay, let's suppose, for example, that Bob measures 1, 0. Okay, so suppose Bob measures 1, 0 in the error syndrome. Okay. Now let's examine the table above. If he measures the error syndromes as 1, 0, then he must have either received this state or that state. In fact, they are the complements of each other, right? So we have A0, 1, 0, and here we have A1, 0, 1. Here we have B1, 0, 1. And on the downside, we have B0, 1, 0. Okay, so, but which one is more likely, we can ask? Well, certainly this one is more likely to happen. It's more likely that that only one qubit gets corrupted rather than 2 qubits get corrupted. right? So the probability of this state, Bob receiving this state, is p times 1 minus p squared. But the other probability, having this state, is p squared times 1 minus p. So it's more likely that Bob has this state instead. So then what should Bob do? Well, Bob corrects the state by applying the not transformation on the second qubit then, right? Since the second qubit was changed during the transmission, then Bob is going to apply, and since this state is more likely to be received in the receiving end, then Bob it's more reasonable to apply this correction, applying a not transformation on the second qubit, rather than applying the not transformation on the first and third qubits. All right, so but this doesn't quite give Alice's original state. I mean, you might ask, well, Alice wanted to send A0 plus B1. So how are we going to get that? Well, Bob applies C0 transformation on the third and second qubits. If we look at the diagram here, taking the first qubit as the control qubit. So assuming that Bob either receives, let me call these I, or maybe star and dagger. Okay. So he either receives the star state or the dagger state. And if he applies the decoding operation, the final state that Bob receives either going to be A0 plus B1 0 0, or it's going to be, if he receives dagger after applying the decoding operation, he will get A1 plus B0 0 0. The last two qubits are the qubits from the encoded state. Okay. All right. So now at this point, Bob doesn't know which state he has, but the important point is that this method has a success probability greater than 1 minus p. The failure probability, that at least two qubits are corrupted by the faulty channel, is less than p. Right? So the probability that Bob fails to obtain Alice's original state is bounded by p squared, whereas it would have been, so this is with error correction, whereas it would have been bounded by p if no error correction had been used, without error correction. So of course with more qubits we apply the same idea here and we get more we get better noise suppression, and the success probability will increase exponentially. Okay, so this is how the bit flip model works. But this is not really exclusive to quantum computation. What's more exclusive to quantum computing is the phase flip error. Phase flip error. Okay, so the phase flip error simply changes the relative phase of a qubit. So if we are given something like A0 plus B1, this gets mapped to A0 minus B1. Or similarly, if we have A0 minus B1, this gets mapped to A0 plus B1. So it changes the relative phase, the sign of the quantum states. So this kind of error, the phase flip error, is not found in any classical error correction because there is no corresponding phenomena for the phase value in classical computing, right? Because the concept of the phase is unique to quantum computing. And though this is a restricted form, in fact, we will see later on that we could have phase defined by generally by a complex number in the exponential form, right? So a phase flip error, in fact, it changes this phase value theta, which is a real number. So that's why we have continuum many different error models in quantum computing. Okay, so to overcome this problem, the phase flip error, again we can use the bit flip channel. In fact, we can use the bit flip model to correct the phase flip error. And one way to do this is to transform the phase flip channel into a bit flip channel. And we do this by changing the basis. Okay, so suppose that we work in the sine basis. Okay, so we turn the phase flip channel to a bit flip channel using change of basis. Okay, so suppose that we work in the sine basis. Okay, the ket plus and ket minus basis. And recall that ket plus is equal to 1 over square root 2, 0 plus 1 over square root 2, 1. And ket minus is 1 over square root 2, 0 minus 1 over square root 2, 1. Okay, so the idea is the same, except that now we work under the sine basis. So the basis change is performed by an application of the Hadamard transform, because Hadamard transformation is simply used to change the basis from the sine basis to the canonical basis, right? So we use the Hadamard transformation and its inverse at appropriate points in the procedure to perform the basis change, and we still use the bit flip error, the error model. Okay, so I'm going to give you the circuit diagram for the phase flip code. So we start with psi, the state that we want to transmit. We have two ancilla qubits set to 0. So we take the first qubit as the control qubit and then apply a C0 transformation on the second qubit, and then take the first qubit again as the target qubit, apply a C0 transformation on the third qubit, and then we apply a Hadamard transformation on each of these qubits. Hadamard transform, Hadamard, another Hadamard transform. And then we change into the sign basis here. Okay. And then we have the phase error here, epsilon phase. This is the faulty channel on which the phase error occurs. And then in the output, we change the basis back into the canonical basis. Hadamard, Hadamard, Hadamard. Okay. And for the decoding, we apply the same procedure in the beginning. And then finally, we take the both of these last qubits as the target qubits, and then apply C0 transformation on the first qubit. Okay. All right. So these are two simple error models for quantum computing: the bit flip error and the phase flip error. But there's a better solution for general errors that could occur in any quantum computation, and that's settled by a 9-qubit short code, and we'll see that in the next video.